What's up, AP Physics C Mechanics students? Welcome back to our Elegant Physics videos. Today's topic, circular motion, part 1, 2.10. So let's jump right in. Consider a particle M of coordinate xy. So this particle, it's located at this location, and this particle is associated with x coordinate and y coordinate. And let's assume that this particle is moving along circular path. The center of the circular path is AB. So also here we have new coordinates for different point. This point is the center of the circle. Now the x component of this point is A, and the y component, it will be B. Now we know that any circle is characterized with a constant, and this constant is the radius r, which is the distance from the center to the circumference. Now the trajectory equation, or equation of a circle, is given by the constraint equation. For any motion with a circular path can be described via this equation. Now x minus a to the power of 2 plus y minus b to the power of 2 equals r to the power of 2, where a and b are the coordinate of the circle, and the r is the radius of the circle. Now, the kinematics of a circle can be expressed in the polar coordinate system. The polar coordinates are given by the r and theta. Instead of describing the motion or the location via x and y, now we will use different coordinate system, which is r and theta associated with r, which is the radius, and the theta, which is the angle that the object make with some reference. So this is actually the angle. So if the object, for example, is located at an angle 90 degree, this is the 90 degree with respect to this reference. This is our reference. And this is the 90 degree, and here is the new location of the object M. So we can write the angle theta in terms of time. So we can have all the possible angles that shows the location of the object. And it is the angle between the line IM and the horizontal line of the equation y is equal b. Now, in Cartesian coordinate system and the polar coordinate system, they can be related to each other via the following transformation. So these set of equations consider to be the transformation between x and r and theta, r theta a, and y r theta b. So to find the x coordinate of the object, we just write r cosine theta plus a, and to find the y coordinate, we just write r sine theta plus b. Let me remind you that the r is the radius, the angle between the horizontal line associated with b and the location of the object. A is the x coordinate for the center of the circle, and b is the y coordinate for the center of the circle. Now, once the function cosine and sine appear in Cartesian coordinates, one should directly think of circular motion. But this is not the end of the story, because it's not considered to be a general rule. The key point is that both cosine and sine should have the same coefficient and the same angle. So let's take a close look on the equation. X is equal r cosine theta plus a, and y is equal r sine theta plus b. Make sure that the angles are the same and the coefficient r, which is represent the radius, is the same. Then you can say safely that this represents circular motion. A useful equation when considering trigonometric function is cosine square theta plus sine square theta is equal to 1. And this equation is widely used. You can call it the Pythagorean sum in trigonometry. The velocity is always tangent to the circle. So this line here, or this vector, as you can see, during the motion of the object, is always making a tangent to the circular path. Now, let me remind you that in the unit circle, we always set the cosine along the x-axis and the sine along y-axis. And usually we use this trick just to memorize the integration and the derivative. So if this is sine, would be minus sine, and if this is cosine, this would be minus cosine. Now, if we rotate in this direction, this is the derivative rotation. So the derivative of sine will be cosine, the derivative of cosine is minus sine, and the derivative of minus sine is minus cosine, and so on. So as long as you are rotating clockwise, then this is the direction of the derivative. Now, what about the integration? For the integration, we use the opposite direction. So the counterclockwise direction is for the integration. So the integral of cosine is sine, the integral of sine is minus cosine, and so on. And moreover, I just want to remind you with the chain rule in trigonometry. So sine, it's considered to be the first layer or the first box. And inside the sine, we may have another function. So for example, let's say we have 2t. So this function is consists of two functions, function of a function, or you can consider it as a two boxes. So we can, to find the derivative, we just apply the derivative on the first layer and then we apply it on the second layer. So let's apply the derivative on the first layer. What is the derivative of sine? We know that from the unit circle, the derivative of sine is cosine. So cosine 2t, we write the same angle again. Now we finished from the first layer. So we did this. Now it's time to apply the derivative on the second layer, which is the 2t. What is the derivative of 2t? The derivative of 2t, this is linear, it becomes constant, so the derivative is 2. So we just write here, but as a convenient way to write this kind of functions, we just move the 2 to be front of the cosine. So in summary, you can think about the derivative here for this kind of functions as if the derivative is spitting outside the derivative of the inner function. So first of all, we apply the derivative on the sine, and then we spit outside the derivative of the inner function. So the derivative of the inner function is 2. And let's take another example, cosine of 5t. Now the derivative of sine 5t, we just apply the derivative on the outer function first, and we know the derivative of cosine is minus sine of 5t. And then we spit outside the derivative of the inner function. The derivative of the inner function is 5. So let's solve exercise 1. Given the position xy of a moving particle is in two-dimensional plane, state for each of the following examples of the governed trajectory is a circle or no. All quantities are in the SI unit. We know that once I catch sine and cosine in my equation, then there is a possibility that this equation presents a circle. But this is not a sufficient condition because it's necessary to have the same angle and the same coefficient. And what do I mean by the coefficient is the number written in front of the cosine. So here, for example, in the first example, we have the same coefficient, but unfortunately we have different angles, so this cannot be considered as circular motion. So no different angles. Now, what about the second one? It seems like the second one is strange a little bit. So we have -1, for example, here. We used to have the x alone. So it's easy. You just remove the -1 to the other hand side, it becomes a +1. Now we don't care about the number here, written here. It won't change the type of this equation because by reordering it, we can get the proper form. Anyway, we just need to check the angle and the coefficient. If they are equal, then this represents a circular motion. We have the same coefficient, we have the same angle, so yes, this represents a circular motion. Now, what about this one? Again, we don't need to evaluate the -3 and -2 because they are present the center of the circle. We just need to check the angle and the coefficient. We have the same coefficient, no different coefficient, so no need to complete. This is cannot be considered a circular motion, a circle. Now, what about the last one? We have the same coefficient and we have the same angle. Now, what about the x over 2 and 2y over 4? Now, we can just rewrite this as y over 2. Since they have the same denominator, then you can say they won't affect the coefficient. So yes, after we simplify the fraction here, 2y over 4, which is y over 2, is the same as x over 2, same denominator. So one can say that the denominator here, since is the same in x and y, then we can realize that it won't affect the result in the right-hand side. What if we have, for example, here 3? Then you must move the 3 to the other hand side and it will may change everything because you know that if you want to move the 3 to the other hand side, you need to multiply the right hand side with the 3. So 3 times the 3, it's 9, the angle. But here, if this is 2 and we keep it as 2, this is another example, by the way. Now, if you multiply 2 to the other hand side, the coefficient may change. So different coefficient, which means different angles. This in case we have different denominator. We need to double check. Uh, Clearly, the denominator may affect the coefficient or not. Now here for this question, let me move to another whiteboard because we need larger area to solve this question. For each of the following examples, determine the speed and the magnitude of the acceleration. So pay attention here to the keywords because here in the keywords, they want me to calculate the speed, and we know that the speed is equal to Vx. So the speed is the Vx squared plus the Vy squared, and the magnitude of the acceleration is now what do we have here? We have the x time equation, the position time equation for the x and the y. Now we know that to find the speed, we need the Vx and the Vy, and the Vx is the first derivative of x over time. So let's apply the derivative here. Now we keep the 4, we don't need it. It's just a coefficient multiplied by cosine. So the coefficient maintain the same. Now what about the cosine? Let us test our work with this unit circle. We know this is the cosine, this is the sine. Here in the opposite direction, we have the minus cosine and the minus sine. And remember always, this direction will be taken for the derivative. So what is the derivative for the cosine? The derivative of cosine minus sine. So I will place the minus here, make some space for splitting the derivative of the inner function. What is the derivative of the inner function? It's a 3, so split it outside. Now, this equation represent or consists of two terms. We applied the derivative on the first term. Now it's time to apply the derivative on the second term. However, the second term represents a constant, and we know that the constant, the derivative of the constant is 0, so minus 0. Now, minus 4 times 3 is minus 12 sine 3t, and minus 0 is equal to the same. So this is the Vx. Let me put it inside the box. Now, what about the Vy? The Vy is the first derivative of the y component over time. So as you can see here, uh, we have the same coefficient as the previous one, and we have the same angle as the previous one. Again, we have another term. The derivative of the second term will be 0 because it's constant. Now, what about this term? You should expect that you will get the same answer, but you may have different angle and different sign and different function. We know that the derivative of sine is plus cosine, so plus outside cosine, but we will get the same coefficient. We must have the same coefficient here. So it's gonna be 12 cosine 3t, so plus 0 or minus 0, because minus 5 it's minus 0. I know it won't make any difference, but we should follow the same order of signs. Now we have the two ingredients to build or to construct our speed. So the speed is equal Vx squared plus Vy squared. So we have minus 12 sine 3t squared plus 12 cosine 3t squared. One can ask himself, where should I apply the square? Do I need to apply it for only for 12, for sine, for 3t? First of all, the 3t is enveloped with the sine, so we don't have access actually to 3t. We just need to apply the square on the sine and on the 12 and on the minus. So let's do it step by step. What is the derivative, or not the derivative, what is the squaring of the minus? It's a plus. So the square of minus is plus. The square of 12 is 144, or you just can keep it as a squared, and I will show you why later. What is the squaring of sine? Sine squared. And the 3t, keep it the same, plus. Now the same here, I'm not gonna write it as 144, I will write it as a 12 squared, because as you can see, we can have a common denominator and we can cancel the square under the square root. So it's better to maintain the square. And the cosine square 3t. Now we can just take the 12 squared as a common factor. What left behind is the sine squared 3t plus cosine squared 3t. Now we know that sine any angle squared plus cosine any angle squared is equal to 1. So actually, this is equal to 1. Now, 1 multiplied by 12 squared is 12 squared, and the square will be cancelled with the square root, and the final answer will be 12 meter per second. Now, we can say that the coefficient, as you can see here, the coefficient will be the same as the final answer, the speed. So we can ignore these steps to find the speed. We just need to take the coefficient, and this is going to be the speed, the coefficient for sure for the Vx and the Vy if they are equal, and they're going to be equal if we have circular motion. Now, what about the acceleration? So we need to find the ax and the ay to find the magnitude of the acceleration. The ax is the derivative of the Vx over time with respect to time. So the Vx is minus 12 sine 3t. So we keep the minus 12 the same. We just apply the derivative on the sine. What is the derivative of the sine? Is cosine. We make sure that we have enough space for splitting the inner function or the derivative of the inner function. Now the inner function is a 3t, the derivative is a 3. Now minus 12 times the 3 is minus 36 cosine 3t. And this is going to be the ax. What about the ay? So we have 12 cosine 3t, and the derivative of the 12 cosine 3t, we keep the 12. The derivative of cosine is minus sine, so we place minus, and again we will have to split outside the inner function. And the final answer for the ay, minus 36 sine 3t. Now you can expect that the magnitude of the acceleration will be 36. Now a is equal ax squared plus ay squared. By following the same argument that I did it for the speed, you can realize that the a is equal to 36 meter per second squared. Now for the second question, x is equal r cosine 2 omega t plus 1. We first find the Vx, which is the dx over time. Now, what is the derivative of 2r cosine? We don't need the coefficient. We just give it the same. We just apply the derivative on the cosine, and the derivative of the cosine is minus sine 2 omega t. What is the derivative of 2 omega t? The only variable here is t, and it's linear, so the derivative is constant, and the constant is 2 and omega. So we place them outside. So the final answer will be 2 times 2 is 4 r omega sine 2 omega t. Now what about the Vy? It's dy over dt. Now we apply the derivative. For sure, the derivative of plus 1 is 0. Forget to add it. Now we have, again, two terms. We just apply the derivative on the first term and then the derivative on the second term. However, the derivative of the second term is 0 because this is constant. Now you should expect that the final answer will contains the same coefficient. However, the function here will be different. The sine becomes cosine, but maintaining the same sign, no changes on the sign because this sign here is a resultant from the sign itself because the derivative of the cosine is minus sign, but here the derivative of the sign is purely plus cosine. You can double check by referring back to the unit circle. So the Vy is equal 4 omega cosine 2 omega t. What about the speed? Following the same argument, the Vx squared plus the Vy squared. So the Vx is minus 4 r omega sine 2 omega t to the power 2 plus 4 r omega cosine 2 omega t to the power of 2, which is equal to, we just applied the square on the sine, the 4, the omega, the r, the sine. However, I'm not gonna write the square of 4 because I may add a bracket to get a common denominator and then to cancel the square with the square root. So let me show you that the square of the minus is a plus. The square of 4r omega is 4r omega to the power 2. The sine square 2 omega t plus 4r omega squared cosine omega t, which is equal, now we can take the 4r omega squared as a common factor. What left behind will be the sine squared 2 omega t plus the cosine squared 2 omega t to the power 2. Now we know this equals to 1, and this is just a typo. We don't need the square. We already implemented the square here and there. Now the answer will be 4 omega r to the power of 2, and we can cancel now the square root, the square root, and the final answer will be 4r omega again. So no need to do all of this work. We just need to take the coefficient, and this is going to be the magnitude of the velocity or the speed. Now, next step, we need to find the acceleration. The acceleration along x-axis is the derivative of the vx with respect to time. Now, the derivative of sine will be cosine. So same sign, cosine 2 omega t. We split outside the derivative of the 2 omega t, and the derivative of 2 omega t is 2 omega. And the answer is 2 times 4 is minus 8. R, omega times omega is omega squared cosine 2 omega t. This is the AX. What about the AY? It's the derivative of the Vy over time. Now the derivative of 4r omega cosine, the derivative of cosine will be minus sine, so we place minus the same coefficient again. No need to double the work. But now the cosine becomes the minus sine. We place the minus outside, so we just need to add the sine to omega t, and this is going to be the AY. If you would like to find the magnitude and using the definition, so we know that the magnitude of A is equal the AX squared plus AY squared. However, I will follow a shortcut. We know that this coefficient represents the magnitude of the acceleration. So the magnitude of the acceleration is 8r omega squared. Now, question number 3. Let's start with the Vx. The Vx is equal to the dx over dt. The dx is the derivative of a sine omega t. We know that the derivative of sine will be cosine, and it will be positive, so plus a cosine omega t. Now the derivative of the inner function is omega. So this is the velocity along x-axis. What about the along y-axis, which is the dy over dt? Same coefficient, no need to double the work, but this time the cosine becomes minus sine, so minus sine omega t. Now to find the speed, which is the vx squared plus the vy squared, you can derive it from scratch. You just substitute, you apply the square. However, you will always get the same coefficient, because here this represents the magnitude of the speed. What about the AX? The AX is the derivative of the VX over time. Now the Vx is a omega cosine omega t, so we maintain that a omega cosine becomes minus sine, and we split outside the omega. The final answer is minus a omega squared sine omega t. What about the AY, which is the dvy over dt? Now, what is the derivative of the a omega sine omega t? We maintain the a omega. the sine becomes cosine, and we split outside the inner function, the derivative of the inner function. So it becomes a omega squared cosine omega t. Now the a is equal ax squared plus ay squared. You can substitute the a omega squared sine omega t here, the a omega squared cosine omega t here. You take the a omega as a common factor and you replace the cosine omega squared with the sine omega squared with 1. However, I'm not going to do that. It will take a long time because I know that the coefficient will be the same answer as the magnitude, so I just write the coefficient. This is the final answer. Okay, so here in this question, for each of the following examples, determine the trajectory equation of a moving particle S whose coordinates are x and y. If the trajectory is a circle, indicate center and radius. All quantities are in the SI. So first of all, I need to find the x and y coordinate of the center and the radius in case the trajectory is a circle. Here we have the same coefficient, we have the same angle, so this trajectory is a circle as well as is here, as here. Now we know that the general form of the equation for the transformation is given by x is equal the radius sine theta plus a, and the radius r cosine theta plus b. Now a and b represent the center of the circle. Now for the first equation, whenever you want to take the a and b, which are represent the center of the circle, in the general form of the equation, let me remind you the general form, x minus a squared plus y minus b squared equals r squared. So as you can notice here, the minus state that we always use the opposite sign of the a given in the equation, of the transforming equation. So minus means opposite sign. And as you can see here, -2 is the coordinate, the x-coordinate of the center. We use it in the equation as a plus. But when we want to extract it, we extract it as a plus. And let me explain why. Now, if x is equal -2 and y equals -5, according to this equation, then if we move the minus to the other hand side, it becomes a plus. If we move the minus to the other hand side, it becomes a plus. And this is why whenever we want to write the equation, we use the opposite sign. So if we want to extract it again, it's going to be -2, -5. What about the radius? Now here the radius is actually 4. We know that the coefficient represents the radius and the radius is 4. Now what about the second question? For the second question, let's start with the radius. The radius is 2r. So immediately I can say that the radius is 2r. So what about the center? Now these represent the center of the circle. So +1 is the x and the -1 is the y, but whenever I want to plug them in the equation, I need to use the opposite sign. So -1 squared plus +1 squared equals the r squared, which is 2r to the power 2. And for the last question, apparently that the center is 0 because there is no plus minus number, even here or there. So the center is 0, 0, and the equation becomes x squared plus y squared equals the radius squared. And the radius is a, so r is equal to a. For repetitive motion, we can always define the following quantities: the period, the frequency, and the angular frequency. The frequency, F, the unit is Hz, and it's defined to be the number of cycles per unit of time or per second. So when I say, or the frequency is 10 hertz, it means 10 cycles per 1 second. So in every 1 second, the object will be able to complete 10 cycles. Now, the period is not about the numbers of completed cycles, it's about the time needed to complete one cycle. So for every one cycle, how much time did I spend? Now, for example, here, the object needs 2 seconds to complete one full circle, and the frequency will be half cycle per second. Here, the object needs less time to complete one cycle, which 1 second. So every 1 second, the object will complete one cycle. And the frequency will be 1 hertz. So for every 1 second, the object will complete one cycle. 2 hertz mean 2 cycles in seconds, 4 cycles in seconds, 5 cycles in seconds, which is much faster. As the frequency increases, the number of cycles per second increases. You can say that the period will decreases. So the largest period is to the right, and the least period is to the left. The opposite will be for the frequency, the largest to the left and the least for the right. This relation opposite or let's say inverse relationship between period and frequency can be described via this relationship. Mathematically, I mean, in this relationship, so the frequency is 1 over period and the period is 1 over frequency. Now, the angular frequency is defined to be omega is equal to pi f or 2 pi over t. So let's start with the variables of circular motion. Variables of motion can be introduced for circular motion and they are given by. Now we're gonna update our variables to include variables related to the angle. We will call them the angular terms. Now for the angular terms, we have the angular position theta and radian, the angular velocity omega and radian per second, and the angular acceleration alpha, which is radian per second squared. So theta, omega, and alpha. The above variables of motion are understood as vector quantities that they have magnitude and direction. The default positive direction associated with circular motion is anti-clockwise. So any motion in this way, the anti-clockwise or the counterclockwise direction is considered to be positive. Any motion in that way, it's considered to be negative. This is the clockwise direction. Now let's make an analogy with the linear terms, the position x, the velocity v, and the acceleration a. Now we will use for the angular terms, the theta, omega, and alpha. Now, what about the equation of motion? You're gonna see some mathematical symmetry or similarity between the linear and the angular kinematics. For the angular one, we can state 2 types of motion, the uniform motion and the uniform circular motion, or the uniform varied motion. Now, for the uniform circular motion, which is equivalent to the uniform motion, but in circular path, or we can write it as UCM, the alpha, the acceleration, angular acceleration is 0, and the velocity is constant, the omega is constant. And there is only one equation that help us to describe the situation, the theta is equal to theta 0 plus omega t. Now we know that if we move the theta 0 to the other hand side, we will able to have theta minus theta 0, which is delta theta, and it's equal to omega t. So we can write directly delta theta, the angular displacement, as omega t. So this represents the angular displacement. Now here the trajectory is a circle and v always perpendicular to acceleration. The direction of acceleration is toward the center here in uniform circular motion, and the velocity is tangent to the path. So if the satellite now moves to this direction, the acceleration is toward the center and the velocity is tangent to the path. Even here, toward the center, and the velocity is tangent to the path in uniform circular motion. What if we have non-uniform circular motion, or let's say uniform varied circular motion? For uniform varied circular motion, the equation of motions are for omega is equal omega 0 plus alpha t. And here the alpha is constant. Alpha, the angular acceleration is constant. Omega is equal omega 0 plus alpha t. Theta is equal theta 0 plus omega 0 t plus half alpha t squared. And this can be written as delta theta is equal omega 0 t plus half alpha t squared. Omega squared is equal omega squared 0 plus 2 alpha theta minus theta 0, or you can write it as omega squared is equal omega squared 0 plus 2 alpha delta theta. And finally, delta theta is equal half omega plus omega 0 t. Or you just can write it as delta theta is equal omega plus omega 0 over t, 2 times t. Now the trajectory, again, it's a circle, but this time V is making a fixed angle, makes with a fixed angle, but not equal to 90 degrees. So the same angle, but not 90 degrees. So A is not toward the center anymore, but V still tangent to the path. And here I'm talking about the velocity and acceleration, not the angular velocity and the angular acceleration. Now, some remarks regarding the uniform circular motion. Even if the object is rotating at constant speed, it will submit it to acceleration. What do we call this acceleration? Usually we call it as centripetal acceleration. This is going to be our topic for the next session. Angular acceleration is a part of acceleration, and this is known as tangential acceleration. So this is just a component of the acceleration, and we call it as tangential acceleration. Acceleration is due to variation in velocity, and the velocity has both direction and magnitude. Along the trajectory of a circle, the direction of the velocity changes, which causes the acceleration known as centripetal acceleration. Now, what I'm trying, let me summarize what I read in the previous section. Now, as you can see here, the velocity kept changing itself, or kept changing its direction, let's say. Whenever I want to change the velocity, I can do that via its magnitude. And when I say magnitude, I mean by the magnitude, the numerical value, or its direction. Or both. I can change the magnitude and the direction, but to change, you need to apply the acceleration. If I want to change the magnitude, I need the acceleration. If I want to change the direction, I need the acceleration. In circular motion, this acceleration that make the magnitude change is the tangential acceleration. And in circular motion, the type of acceleration that make the direction change is the centripetal acceleration. And these two types of accelerations are crucial in circular motion. So one of them will change the magnitude and the other will change the direction. And actually, we will cover these two types of acceleration in the next topic. Now, let's keep moving. We're going to solve some problems now. Now, an object with unknown initial velocity has a constant acceleration with the components ax, it's a constant, 8 meters per second squared, and the ay is 0. Which of the following possible expression for the position of this object in meter for both x and y direction as a function of time? So we need to indicate which one of these equations is suitable or are suitable for the previous claiming that the ax and the ay, one of them is constant, the other one is 0. Now, the easiest way to do that is by using our trick that the 0, the constant, then the linear, then the quadratic. We just need to match the a, v, and x to one of these, and we can realize or we can track what will be the velocity and the position. So we know here for the ax, let's start with the ax. The ax is constant. So by following the order, the velocity is linear and the position should be quadratic. So remember that the position, we found the position is quadratic. It should be quadratic. Now, what about the ay? The ay is 0. So the a is 0. Then the v will be constant and the position will be linear. So the y will be linear. Should be linear. Now, any equation that reflects these two facts, then it will be our possible answer. No, the x should be quadratic. So not a, because x is not quadratic. X is not quadratic. Now we're left with the three choices. And the y should be linear, so it's not quadratic. The y cannot be quadratic. Cannot be quadratic. It should be linear. So the correct answer is D, because D has quadratic x and linear y. Now next. Particle moves in a circle in such a way that the x and the y of its motion given in meters as a function of time. So we have the x, we have the y in meters. What will be the radius? We know that the radius will be the coefficient, and the radius will be 5. Now again, we have the same equation, 5 cosine 3t sine cosine 5 sine 3t. Which of the following is true of the speed of the particle? So we need to know what is the speed. To find the speed, we first apply the derivative. So the Vx is equal. Now the derivative of cosine will be minus sine, so minus 5. We split outside the derivative of the inner function, sine 3t. And the answer is minus 15 sine 3t. We apply the same thing here. The Vy is equal. The derivative of sine is cosine, so 5 times 3 cosine 3t. We split outside the inner derivative of the 3t, and the derivative of 3t is a 3. We split it outside. And the answer is 15 cosine 3t. Now, since this is MCQ, I should do this faster. We know that the speed is Vx squared plus Vy squared, and it's gonna be 15. It will be the same as the coefficient meter per second. This is the speed. So the answer is B, but why B, not, for example, D or E? Because D and E are also involving 15. Now, the thing is, the speed will be constant, and it's always going to be in circular motion 15. And for D and E, they are claiming that it will oscillate, so it's not called circular motion, and will be a range. So first of all, the type of motion is not oscillatory motion, it's circular motion, and it won't be in between a range. The speed will be fixed under the same value always and forever. Now, in an experiment, student records horizontal and vertical position of an object as a function of time. The student claimed that the data show that the horizontal acceleration is approximately 0 and the vertical acceleration of the object is not 0. Which of the following evidence statement will support this claim? Now, according to this data table, we have information about the horizontal position and vertical position, and we can directly relate it to the acceleration via the trick. So we know that 0 will give us constant, then linear, then quadratic. If the quadratic, okay, if the claim is true, then if the acceleration, if the claim, which means the acceleration, the horizontal acceleration is 0, if the acceleration is 0, then the x is linear because the velocity will be constant. So the x must be linear. X is linear. So if the acceleration is approximately 0, then the position must be linear. So position linear. Non-zero acceleration, it can be constant or even linear. So for non-zero acceleration, for the vertical one. So it can be constant or even linear. But since we are dealing here with the experiment, most probably it's gonna be constant and not linear. So let's find out the possible choices. That the horizontal position is constant and the vertical position is changing. Okay, so let's evaluate what is going on with the horizontal position. For the horizontal position, if it's linear, then it will increase in constant or decrease in constant way. So for example, every step for every second, the position will increase by 1 or by 2 or by 3, but this value will be fixed for the all other possible values. So let's find the difference now, because the first difference, if the first difference is the same, then this could be linear. So here the difference, let's write the approximate value of the difference. So 1 and 2, I know this is 2.1, but I will take the approximate. It's 1, and here the difference is 1, and here the difference is 1, and there is 1.1, but I'm gonna write it as 1 because we are dealing here with a experimental method or experimental data. So it's possible to have a variation in the values, slightly difference in the values between the different time intervals. So in general, the difference is 1, so the horizontal position is linear because the first difference is constant. Now, what about the vertical position? Again, I will follow the same strategy and I will see if we have fixed value or no. So 3 minus 2 is 1. 3.5 minus 3, 3.5 minus uh, 3 is 0.5. Now then 3.5 and 3.5 is 0, 3.1 and 3.5 is approximately 0.5, approximately. 2.1 and 3.1 is 1, 0.5 and 2.1 is 1.5. I will stop here, no need to complete all the data. I just need to find the trend of that the data follows or follow. Now, then we're going to find the second difference. If I found the second difference is constant, then this could be quadratic. Now 0 0.5 and 1, 0 0.5, 0, 0 and 0 0.5, 0 0.5, 0 0.5 and 0, 0 0.5, 1 and 0 0.5, 0 0.5, 1.5 and 1, 0 0.5. So it seems like this is the second difference. And whenever the second difference is constant, this is a quadratic. We took this in AP pre-calculus. So if you have a certain type of data and you found the first difference to be constant, this data represent a linear relationship. If the first is not constant, then try to find the second difference. If the second difference is constant, then this is quadratic. If the third difference is constant, then this is cubic, and so on. No need to test the cubic because we have the second difference to be constant, and this represents a quadratic relationship. So the position is not constant, it's a linear, so not A. The position changing and the vertical position is constant. The vertical position also is changing, so it's not B. The horizontal position is changing. No, it's at a constant rate. Yes, perhaps maybe this one it could be correct the answer. And the vertical position is changing at non-constant rate. Yes, it's a changing but not linearly. So possibly C. The horizontal and the vertical position are both changing at constant rate. No, they are behaving different ways. And also E, no, because they are behaving different way. Behaving in different way. Okay, an object starts from rest at the origin on the xy coordinate system and has an acceleration with the component ax and ay. So we start from rest with a zero velocity. So the v initial is equal 0 along x-axis. The v initial along y-axis also is 0. The acceleration at the origin is a, and here is a. So the magnitude of the acceleration, can one say that ax squared plus ay squared, which is equal to a plus a, and the answer will be 2a squared, which is equal to a radical 2. So the square root of 2 is radical 2, and the square root of a squared is a. Let's keep this in mind. So after t seconds, the displacement and the velocity of the object are delta d1 is the displacement and v1 is the velocity after t seconds. Now the object is stopped and returned to the origin again. The object then starts from rest again with the acceleration. Now we have different acceleration. Let me find out what happened to the acceleration. So the new acceleration is the new magnitude, particularly I'm talking here about the magnitude of the acceleration. Ax squared plus ay squared. The ax is 2a squared plus 2y squared. So we will have 4a squared plus 4a squared, which means 8a squared. And if we took the square root of 8, it's going to be 2 radical 2, and the square root of a is a. So actually, as if the acceleration has a change by 2 from a radical 2 into double a radical 2. So the new magnitude of the acceleration is double the old acceleration. This is very, very important result that it may help us to find what will happen to the magnitude of the displacement and the magnitude of the velocity. So the acceleration in the first trial has been changed into double of the acceleration in the first trial. So double the acceleration now, because it was a radical 2 and now it becomes 2 a radical 2. So double the old acceleration. Now, what will happen to the displacement and the velocity in this case, but in terms of delta d1 and v1? So let's find out what will happen to the velocity and then the displacement. We know that the velocity is equal v0 plus at. We cannot apply directly the factor of change here because we have the v initial plus, and factor of change cannot be applied for plus and minus. However, we started from rest in both trials, so we can cancel this term, and now we can use this equation for the factor of change. What happened to the acceleration? It's doubled by 2, so actually 2. And what happened to the time? We use the same amount of time here in the second trial, and the velocity will increase by 2. So it won't increase by, for example, radical 2, radical 2, radical 5. It will increase by 2. What about the delta d? v0t plus half at squared again. We cannot use it for factor of change unless we cancel this one. And yes, we can cancel it because it starts from rest. And the factor of change will be delta d applicable here, half at squared. Remember, any constant should be replaced by 1. So half should be replaced by 1. The a has increased by 2. And the time will be replaced by 1 because we have used the same amount of time. And the final answer will be 2. So the displacement will increase by 2. And the correct answer will be E. If a particle moves in a plane so that the position described by function x, a cosine omega t plus, and y is equal a sine omega t, the particle is, we have the same r and the same angle, which means we are dealing here with circular motion. So is this motion is constant speed or varying speed? No, it's constant speed. And the speed will be, if we apply the derivative, it will be a omega. So constant speed. And the correct answer is A. Now, the equation, which pair of equations can describe the path of particle moving with the zero acceleration? The acceleration is zero. Here in circular motion, always we have acceleration, so it cannot be something related to circular. Now, to have zero acceleration, the position, let me use the trick. Zero, constant, linear. No need for the quadratic, I'm not gonna need it. So acceleration, velocity, and x. The acceleration must be zero, the velocity constant, and the position is linear as well as y. Because when I say uh, acceleration is zero, I mean by the acceleration along x-axis and the acceleration along y-axis, both of them are zero. So the y should be linear and the x should be linear, and this can be found here, yes. To the power 1 to the power 1 means that the equation is a linear equation, and x and y here are both linear, so the zero for the acceleration will be in this situation. Now, an object is moving in the xy coordinate. The components of the object velocity are Vx is given by this time equation, and the Vy is given by this time equation, as well as we have the acceleration equations. Which of the following factors best represent the velocity and acceleration at time 2? So we just need to put the time inside. Now, for the first one, the Vx is 5 meters per second, and it will be directed in this way. This is the Vx. We just need the Vy to complete the picture. The Vy is equal 3t minus 6. So 3 times 2 minus 6 is equal 0. So the Vx will be directed to the right because there is no any Vy components, which means the V itself is to the right. So it's not down, not down, not left. It can be D or E. What will determine the correct answer is the acceleration. So let's find what will happen to the acceleration. The acceleration along x-axis is given by 2 minus 7, which means minus 5. So it will be minus 5. What about the acceleration along y-axis? So acceleration along y-axis, we just substitute the time there. 4 times 2 minus 2 equals 4 times 2 is 8, minus 2 is 6. So it's going to be 6. Now, therefore, the direction of AY is upward. Now, since AX is to the left, AY is upward, then A will be the diagonal of the rectangular shape formed by AX and AY. And the direction of A will be exactly in this way, which means that E is the correct answer. A small particle started from rest, so the initial velocity is 0. And from the origin, so the x0 is equal 0, the y0 is equal 0. And the travel along xy plane, its acceleration along x-axis is 2, and the acceleration along y-axis is 1. So ax is equal to, and the ay is equal to 1. We need to know what is the x coordinate if the y coordinate is a 12. So we know that the y coordinate is 12. What will be the x coordinate at this y coordinate? We know that the linkage between the y and the x coordinate at specific point is the time. So if I know the time, I can use it to predict what will be the position along x-axis. So let's find out the time when the object has this coordinate, 12 meter. Now the y is equal y0 plus v0 t plus half at squared. Now we started from the 0 with the rest plus half. The acceleration along y-axis is given by 1, and the time is t squared, which means 0.5. Half times 1 is 0.5 t squared, and the y is 12. So we divide both sides over 0.5 and take the square root to get the time. And the time will be 2 radical 6 seconds. Now we use this time to get the position. Now, since here we have this constant acceleration, so again, we can use this equation, the quadratic one, to get the position at specific moment of time. So plus v0xt plus half at squared. Now the initial position is 0, the initial velocity is 0. We just need to use the acceleration, which is 2, and the time, which is 2 radical 6 squared. And the answer here will be 24 meter. So the correct answer is D. And that's it for today's lesson on motion on 2.10 circular motion part one. Thank you for joining me. See you next time.